So in this related rates problem, we've got a reservoir that's in the shape of a cone. And so here's our cone. The vertex is down, and the reservoir is 6 meters deep and has a radius of 45. Ooh, so this is not to scale. It's actually very shallow. So they're right when they say it's shallow. And we want to find a relationship between, we know that the volume is draining out, so we know that dV dt is, we're losing volume from the tank. It's negative 50 meters cubed per minute. So we know dV dt, and we're looking for how fast is the water level falling when the water's 5 meters deep. So as this tank drains, then we want to know, if we keep pulling out the same amount of water per unit time, then how will the height of the tank be falling? We're looking for a relationship then between the volume of water in the tank and the height of the water in the tank. We know for a cone the volume is 1/3 pi r squared h. But what's happening here is that as the water drops, so as the water goes down, not only is the height of the water changing, but the radius is changing. So this relationship, actually the radius is sort of automatically adjusting as the height comes down. So let's see if we can find a relationship between the radius and the height. You can see if we kind of pull this out, this little cross section, and look at it. So this is the depth of the tank, which is 6 meters, and then this is the radius, not to scale, which is 45. Now when the height falls down to some new value, h, then we have a new radius. But I can see that there's a relationship here because we have similar triangles. This small triangle is similar to the larger triangle because both triangles share that angle. They both have a 90-degree angle, and since the sum of the angles has to be 180, that would mean that these two angles have to have the same measure as well. When two triangles have all the same angles, then those two triangles have to be similar. So, and one nice thing about shapes that are similar is that ratios of corresponding parts have to be the same. So if I take, say, the ratio of the radius to the height of the smaller triangle, that's got to match the ratio 45:6 on the bigger triangle, because these parts correspond and h and 6 correspond. So that tells me that the radius is 45/6 of the height, or let's see, both of these are divisible by 3, so the radius is 15/2 the height. I can use that to get a relationship between the volume and the height alone. So the radius squared is going to be 225, because 15 squared is 225. 2 squared is 4, h squared, times another h, it's going to give me h cubed. Okay, so now I have the relationship that always holds just between the volume and the height. So I had to think about that because in this case, as the height falls, the radius adjusts automatically. So we have a relationship between just those two quantities. So they're asking about dH dt, so I'm going to differentiate both sides with respect to t. On the left we get dV dt. On the right, the 1/3 and the pi and 225/4 are constants. We take the derivative of this and the 3 comes down. So that's going to, we're going to have 225/4 times pi. When the 3 comes down, it wipes out the 1/3, so I'm not going to write that, but we'll have h squared times dH dt. Okay, and do I know enough? Yeah, so I know what dV dt is. It's minus 50, and we have 225/4, and we have pi. And at this particular instant, the height we're told is 5 meters. So we have 5 meters times 5 meters times dH dt. That's enough information for me to solve for dH dt. What I'm going to do is I'm going to multiply everything by 4. 4 times negative 50 is negative 200. Multiplying this by 4 wipes that out, so I have 225 times pi times 5 squared times dH dt. Now I can see I need to get dH dt alone. I'm going to have to take my negative 200 and divide it by 225 and pi, and 5 squared is 25. Of course, let's see, 25 goes into 200 8 times, And so we get negative 8 over 225 pi. Yeah, and that's going to be in meters per minute, because on this side this was meters squared and that was meters cubed per minute. So meters cubed divided by meters squared will leave meters per minute. So that's the rate of change of the height. Now the question is, if we have the rate of change of the height, can we find the rate of change of the radius? Remember, the two are tied together by this relationship. The radius is always 15 halves the height. So if we differentiate both sides, we get that dr dt is 15 halves dh dt. And so we can plug that in. Let's see, we figured out that dh dt was negative 8 over 225 times pi meters per minute. And 15 goes into 225 15 times, because that's where the 225 came from, was 15 squared. And 2 goes in here negative 4 times. So we have altogether then that dr dt is negative 4 over pi meters per minute. Done. Let's do another. Suppose that a drop of mist is a perfect sphere, okay, and through condensation the drop picks up moisture at a rate proportional to its surface area. So we have this drop of mist here, that's this perfect sphere, and let's see, we have, I guess, other water molecules around here, and so they stick to the surface and make this grow. So the drop picks up moisture at a rate proportional to its surface area. Okay, so I guess that would mean that the let's see, the volume is going to be 4/3 pi r cubed, and we're told that dv dt is proportional to the surface area, and the surface area is 4 pi r squared. Okay. So now I think this would be enough to find out how the radius is increasing. Okay, let's look at that. So here's a relationship that always has to hold true, right? So I think this is going to tie dv dt to dr dt. If we take the derivative with both sides with respect to t, on this side 4/3 and pi are constants, and then the derivative of r cubed would be 3r squared dr dt. But we also know from this that the rate of change of the volume is picking up moisture proportionally to 4 pi r squared. Let's see, so if I simplify, on the left hand side I have 4 pi r squared dr dt, and on the right hand side I have k times 4 pi r squared. There's a 4 pi r squared multiplying both sides, so if I divide by it I get that dr dt is equal to k. That's what they ask us to show, right? That the radius increases at a constant rate, and we've got it. Dr dt is equal to that constant k. The constant's actually the proportionality constant that said dv dt is proportional to the surface area. It's picking up moisture at a rate proportional to the surface area. Let's see. Highway patrol plane flies 3 miles above a level straight road at a steady 120 miles an hour. The pilot sees an oncoming car and with radar determines that at the instant the line of sight distance from the plane to car is 5 miles, the line of sight distance is decreasing at a rate of 160 miles per hour. Find the car's speed along the highway. Okay, so we got a plane flying along here, so let me draw my little plane here. Okay, it's flying along at a steady 120 miles per hour, and the pilot sees an oncoming car. So he's above this level straight road, and here's our car coming towards us. And let's see, we know that the distance between them is decreasing at a rate of 160 miles per hour. So if we look at the straight line distance s between those, ds dt is negative 160 miles per hour. So we want to know how fast is the car going. Okay, so we want to know what is, if we call this distance c for the car, right, we want to know what's dc dt. Right? Now, I can see that there is a right triangle here, and we've got this length c, right? It's 3 miles above this level, so if it's just staying at the same altitude, that number will be constant. And so the relationship between this number c and this vertical, let's see, that would be 3 squared, and that's going to be equal to hypotenuse. Let me call this distance s, the straight line distance between them. So we have that relationship. So we have a relationship between the rate at which the distance between these two, this straight line distance is closing, is decreasing, right? Ooh, that includes also the speed of the plane. So when we find this number, we're going to have to take out the speed of the plane to get the rate at which the car is going along here. Okay, anyway, we have a relationship between the straight line distance, and we know how the straight line distance is changing, and this quantity c, which is related to how fast the two are approaching in terms of on the level here, how fast the shadow and the shadow of the plane and the car are approaching. So let's differentiate both sides. We'll get 2c dc dt. Derivative of 9 is a constant, and then we'll get 2s ds dt. And we're interested in dc dt. So dc dt, if I divide both sides by 2c, I get s over c ds dt. Okay, so good. Now we know at this particular time, at this particular instant, when he measured this rate, that c was 5, right? So oh no, that s was 5. So we know that s was 5. Ooh, that's good, because this would be a 3, 4, 5 right triangle. So at that instant when it was measured, c was 4. So now we know that dc dt at the particular instant we measured, s was 5, c was 4, and ds dt was negative 160. Okay, and if we divide negative 160 by 4, we get negative 40, and 4 times 5 would be 200, so we get negative 200 here. Okay. We said this is just the rate at which the shadow of the plane and the position of the car are approaching along the highway, right? But we know the plane is responsible for 120 miles per hour of that. So the gap between them is closing at a rate of negative 200 miles per hour, but the plane is responsible for 120 of that. So the car's speed must be the rest. So the car's speed has to be, let's see, the rest of that would be negative 80 miles per hour. Okay, so the car is moving at 80 miles per hour.